Yeah.
Okay. So yeah, welcome students. This is the CIVE Department Seminar Series, and it's my great pleasure to introduce Dr. Yemi Adelaide. He's an assistant professor at UC Irvine, and he earned his PhD from UC Santa Barbara in 2015. And after his PhD, he was awarded a very prestigious NRC fellowship from the National Academies and did his postdoc at the US EPA's National Health and Environmental Effects Research Lab in Rhode Island. And so his research focuses in environmental engineering, specifically environmental nanotechnology, and also looking at emerging contaminants like microplastics and perfluorinated compounds. And it looks like today he'll give a talk on using nanoscale iron for pollution control. So I think we're ready to start. Yummy. Thanks.
All right. Thank you so much, Dr. Stacy Louis, for inviting me and for the introduction. And hi to everyone. I cannot see you, but I believe you're there. So I would like to start with this survey, if you don't mind. I'm guessing you are all familiar with Poll Everywhere. And the question is for you all to rank each of these activities based on how much water you think they use. So if you think that aquaculture is the one that uses the most water on a daily basis, then you should rank it higher than the others. So the link to the survey is in the chat, and you can also see it at the top of my screen. So once I start to see some response, I would know that people are taking it, and I can see what you all think. So again, you might have to use your phone or maybe on your laptop. I just posted the link in the chat, and it's also at the top of my screen. So it's paulev.com, my first name, and Adele 576, and you should see the survey and you should be able to take it. But let me know if you cannot take it for any reason, if it's not working or not showing up.
It's not working, I think.
It's not working. Okay, that's not good. Can you try again? But do you see it? Here we go. So somebody has been able to make it work. Okay. Trying to keep an eye on time. So the question again is, which of those activities you should rank them based on how much water you think they use. All right, so we have about 9 responses. I would just maybe wait. We have 28 people. Maybe once half of you are able to tell me what you think, we can move on. Or maybe we can actually move on now. Okay, so we have about 11, 12. Okay, so of course, I don't expect you guys to have the right answer. I know the answer. If I didn't check it out, I probably would answer correctly either. But it seems most of you believe that the public water supply, which is essentially how we all get water from our centralized treatment plants, is the biggest way water is taken out of the water cycle and then brought into our lives. And after that, you think is irrigation, which is essentially farming and livestock and so on. No, you're not correct, guys. Thermoelectric power actually uses the most water. So that's what this next slide says. So you can see thermoelectric power uses 133 billion gallons of water per day. It's a lot, but right after that is irrigation, which is another word for farming. Okay, so farmers are the next big users of water. They use 118 billion gallons of water on a daily basis. And based on the coloration, you can see that about half of the water comes from surface water sources, and the other half comes from groundwater sources. So this is another graphic to just show you water use in the US at the state level. So what I like most about this graph is they arrange the water use based on uses, the different activities, as well as according to states. So from the westmost state to the rightmost state. So from Hawaii all the way to the Virgin Islands. And what's interesting here is that most of the western states, California is the tall one, followed by the next tall one, which is you guys in Texas. Most of our uses are irrigation. Okay, and on the eastern side of the country, most of the use of water is for thermoelectric power. And one of the reasons why we use a lot more water for agriculture on the West Coast is the fact that we have less rainfall. So in addition to that, we have droughts. California has been in a drought for some time now, and we do produce crops, but it's not like we produce all the crops in the country. So the Western US accounts for about 46% of all the crops that is harvested within the US, but we use 84% of the water for irrigation. So in other words, on the East Coast, they also produce about 54% of the crops, but they only use less than 20% of the total water that goes to irrigation. And that's just to say we are water stressed. And the fact is that the 84% doesn't even cover all the water needs of agriculture. And that has led farmers to look into non-traditional sources. So the traditional sources would be groundwater and surface water, but now they are looking at maybe reusing treated wastewater from wastewater treatment plants, from industrial wastewater. And that way they can maybe meet the actual demand for water. And this is not a new idea. In fact, here in California, about 46% of the total water used for irrigation comes from treated wastewater, okay? And that's, well, it's good and bad. It's good in the sense that wastewater is guaranteed. There would always be wastewater. So it's not like they think it will go down tomorrow. It's guaranteed, right? In addition, the environmental impact of using treated wastewater cannot be as high as coming up with a brand new water treatment facility or something like desalination. In addition, there are some nutrients in treated wastewater that plants might be able to use, but there is also pretty nasty stuff in wastewater that we probably don't want to get to crops, particularly food crops. So there is need for some treatments if we are going to keep using wastewater, particularly for crops that end up as foods. And if you're kind of familiar with treatment systems, activated carbon seems to be the gold standard for water treatments all over the world, right? So if you make another material and you say this is good for treatment, it has to perform better than activated carbon for it to be seen as something valuable. So we decided to check if activated carbon can actually play a role in making recycled wastewater reusable for agriculture. And the way we wanted to answer the question wasn't to go straight for wastewater. It was to say, let's simulate something simple. So we decided to put together a metallic contaminant, copper, as well as nutrients, phosphate. So these would typically come as runoff from agriculture. So that question again is, can we reuse the runoff from agriculture, wastewater generated generated from agriculture, can it be reused for irrigation on the farm? And the next slide shows what we found with granular activated carbon. So this is the data for phosphate removal capacity of GAC. And you see that when phosphate is just by itself, it barely gets to 10 milligram per gram removal. And when the second contaminant is present, the capacity of GAC goes down. Similarly, when we measure copper, when copper is by itself, it's about 17 milligram per gram in terms of the absorption capacity. But when phosphate is also present in the system, it's below 15. And before I move on, does anyone want to guess why there is a decrease when a second contaminant is present? Feel free to unmute yourself, or you can just send a text in the chat and tell me what you think. I'm not saying you should know the right answer, but if you were to guess, why is the performance of GAC decreasing when a second contaminant is present in the water? Any idea? Any guesses? Yep, so thank you, Ryan Matthew. Ryan Matthew says competition with a second contaminant for active site. And that's a great guess. GAC works via adsorption. So if you have another contaminant, then they will both be competing for space. But we thought without competition, this performance is poor. Okay, 10 milligram per gram of GAC removal, 15 milligram per gram of GAC removal is poor. So that's where we decided to see if nanoparticles can potentially work better in this type of system. And the nanoparticles we used are called nanoscale zero valent iron. So it's just Fe in the zero valent state, or particulates, and the size is in the nanoscale, and sulfidated NZVI, which is essentially when the NZVI was being prepared, we added a source of sulfide so that there is some FES species. So this table summarizes the properties of the two nanoparticles. With sulfidation, the size increases, and that also means the surface area decreases, and you can see some of the faces of iron in the two nanoparticles. So NZVI has a core of zero valent iron and a shell of iron oxide, while SNZVI is not a core shell material, it's a mixture of zero valent iron and sulfide species of iron. So real quick, this is what we found when we replaced GAC with the nano iron particles. Without any treatment whatsoever, we don't see removal of phosphates, or even when we have copper in addition to phosphates, there is no removal over 4 hours. When there is NZVI and SNZVI, we see that the amount of phosphates that is measured decreases, and after about 4 hours we have just about 60% of the initial phosphate concentration left. Now here's where it gets interesting. When we now add copper to the phosphates with the NZVI and SNZVI, we see complete removal of both contaminants within about 40 minutes, and by 4 hours at the end of the experiment, they are both gone. So this was an interesting result because unlike GAC, where an additional contaminant decreases overall performance, what we're seeing here is that an additional contaminant improves the overall performance. So to put some numbers to what we are looking at, we model this result using the first and second pseudo first and second order kinetics models, and we see a better fit with a pseudo second order kinetics model. Right over here, you can see the capacity of the nanoparticles for the two contaminants, and particularly when there is copper present in addition to phosphate, we see the capacity for removing phosphate is really high. And if you want to get what I mean by really high, so here's a plot that shows the capacity of GAC for phosphate with and without copper. So with copper, the capacity is 0.005 milligram per meter square of the surface of GAC, but you can see that with the 2 nanoparticles, we are talking about 2 to 3 orders magnitude higher in terms of removal. But this is for phosphate. So what about copper? We had to measure the two independently, but the story is actually quite similar. When there is no treatment, there is no removal over 4 hours. When we use NZVI, we see about 20% removal. When we use SNZVI, we see about 60% removal after 4 hours. When we add phosphate and we measure copper removal, we remove the whole copper within about an hour, whether we use NZVI or SNZVI. So the result is pretty consistent. It's like this system needs more contaminants to perform well, which is absolutely opposite what you would expect in a GAC system, like I already said. And again, this follows the pseudo-second order kinetics very well. Again, if we compare the performance of GAC for copper removal using the surface area normalization, the nanoparticles are at least 2 orders of magnitude better than GAC. So this got interesting. We really wanted to understand what the mechanism is. How come this system is performing better when there is an additional contaminant? So we went back to the basic chemistry of nanoscale zero valent iron. It oxidizes to iron 2, usually, which also leads to production of electrons. Electrons cause reduction of metals, but we wanted to know what Fe2 does, particularly when when copper and phosphate are both present. So one way to tease that out is to repeat the experiment, but decrease the amount of Fe2 plus that is available. And the way we did that is by adding phenanthroline to the reaction. And phenanthroline actually is a complexing agent. It's a ligand, and it's a good ligand for iron. So it pretty much decreases the amount of Fe2 plus that is present. So here's a summary of what we found. When we repeated the experiments, we found the same results, but when phenanthroline is present, there's no impact on removal of copper by NZVI, but the removal of copper by SNZVI was impacted. And that led us to really conclude in a way that the removal of copper by NZVI is primarily through reduction. All right, but we could also assume that the removal of copper by SNZVI is through Fe2 plus, but we've done additional studies, and what we concluded from this particular result is phenanthroline can actually also complex with the surface of SNZVI, specifically with the iron sulfide portion of SNZVI. So it's pretty much covering the surface of the particles, and the particle is just ineffective. It's there as if it's not there because its surface is pretty much complex by phenanthroline. Now, when we look at the phosphate side, when there is no phenanthroline, this is the performance of the 2 nanoparticles. When phenanthroline is present, the removal of phosphates is negatively impacted. So this clearly tells us that Fe2 plus plays an important role in phosphate removal. Now, when we now mix the 3 components, which is copper, phosphate, and the nanoparticles, here you see the remarkable increase in performance like we saw in the data I showed earlier. However, when phenanthroline is present in that system, the performance of NZVI decreases somewhat, which tells us there may be some contribution of Fe2 plus to the removal of copper. But again, SNZVI is just not working because its entire surface is covered by phenanthroline. And the story is similar for phosphates. when there is no phenanthroline, they both perform equally well. When phenanthroline is there, the performance goes down, which tells us that Fe2 plus probably plays a key role, whether it's NZVI or SNZVI, for the removal of phosphate. The solids obtained from the studies were also characterized using XRD, like I'm showing you here, and XPS, which I will show in the next slide. And based on this characterization, we can actually come up with equations for the reactions that are occurring. So we do know from the XRD that the iron is able to reduce copper, and that's thermodynamically favorable. But it's not just reduction to copper 0, we also have reduction to copper 1 states. In addition, the dissolved iron formed can actually complex copper as well to form this precipitate here. And on the SNZVI side, the reactions are very similar, but in addition, there is also a precipitation with iron sulfide, in addition to the precipitation with iron 2 plus. And for phosphate, what XRD tells us is that there is the formation of iron 2 hydrogen phosphate, which is also a precipitate. So iron 2 has to be there for phosphates to be removed. And this is the primary mechanism for the removal of phosphate. And like I said, we also did XPS analysis, which I am showing you here. But the story from XPS is very similar. It actually just confirms the story from XRD. And with these analyses and meet-Q modeling, we were able to come up with a mechanism to explain why the two contaminant system, we were seeing better performance than when the individual contaminants were present. So please follow me here. So here is NZVI, iron core inside and the oxide on the surface. So for the removal of copper, we think that adsorption is occurring because of electrostatic attraction. I also showed you already that there is reduction of copper 2 to copper 1 and 0, and that leads to the production of Fe2 plus. Okay, and there is also dissolution of Fe2 plus. So all that Fe2 plus goes to the, well, not all of it, some of it goes to co-precipitation. So we have this precipitate formed, and on the phosphate side, there is also some surface adsorption. There is surface complexation. We confirm this via meet-Q modeling, but the most interesting reaction is the reaction between Fe2 plus and phosphate, which leads to the precipitation of iron 2 hydrogen phosphate. And what makes this important? If you go back to the copper side, the byproduct of many of the reactions that lead to copper removal leads to the production of Fe2 plus. So here as an example, and so Fe2 plus is a product of copper removal, but at the same time, it is a reactant in phosphate removal. So if you just look at your, try to remember your basic chemistry. You have an equation where you have reactants and products. If you are taking out one of the products, based on Le Chatelier's principle, you are essentially driving the reaction to the right. So every time phosphate takes some Fe2 plus and precipitates FeHPO4, it is driving the reaction that leads to removal of copper. And we think that is exactly how the two contaminants are promoting the removal of each other, because the product of the removal of one is the reactant for the removal of the other. For the sulfidated iron, the story is not much different. We have adsorption, we have reduction, we also have displacement. All of that generates some dissolved iron, and some of the dissolved iron goes to precipitate copper. There's also the second co-precipitation, which also generates some dissolved iron, and that iron now goes to the the precipitation of phosphate. So again, the product of copper removal is a reactant for phosphate removal, and that way they are both synergically being removed essentially. So we think that's the story here, and that's why we think that NZVI is way more effective when the two contaminants are present. And the other part of this study was we decided to use artificial neural network to model the results to see if we can actually have some mathematical relationship between the input parameters and the output. And the input parameters here are things like the dose of nanoparticles, the concentration of the contaminants, the pH of the solution, whether or not humic acid is present, and so on. And the output is the removal efficiency for both copper and phosphate. So we can input our experimental data if we collect enough mechanistic studies data, and based on what we input, ANN can develop some mathematical correlation. And the cool thing about that correlation is it also generates a weight for each of the input parameters, and that weight sort of represents how important each parameter is. And based on the weight, if you put in some new input, it can use the function developed from the training to predict a new output. So using ANN, you don't even necessarily need to understand the mechanism of the reaction. If the relationship between input and output are not linear, it's not really a big deal. But in our case, we do understand the mechanism, but ANN was a tool for us to also do some prediction. So here is what our architecture looks like. You might be hearing some background noise. It's a little bit windy here today, and I hope we don't lose power. In any case, this is our architecture. So these are all the input parameters, nanoparticle dosage, the ratio of sulfur to iron, and the contaminant concentration, and so on. And another thing I like about this particular work is we were able to simultaneously predict the efficiency of the removal of both copper and phosphate, which is different from predicting one at a time. So we went ahead and confirmed how well the function we developed worked. Here is a plot made from experimental data showing the efficiency of copper removal based on treatment time and SFE ratio. Every other factor held constant. And at the bottom is just a reflection of the 3D graph. So when the treatment time is 0, there's really no removal. But as you have more treatment, you have more removal. And intermediate SFE ratio particles don't perform as good as NZVI. And when the sulfur ratio is as high as 0.28 molar ratio. And what was predicted by ANN is very similar. So you can see there is a lot of similarity between these two plots. The difference between them in terms of the root mean square error was about 3%. So there's just a 3% error chance by the function we came up with. So that was for copper. This is for phosphate. It's essentially the same thing. So we ended up having an ANN function that can effectively predict the performance of our nanoparticles based on different experimental conditions. And the last thing we did was to now ask the question, can we put a weight? Can we put some relative importance to each of the input parameters? And we use this equation is popularly called the Garson equation. So W here is the weight that comes with the function we developed. And this is what the result looks like. It's essentially a relative importance number. So what this is telling us is for copper removal, the most important factor is this factor here, which is time. And for phosphate removal, the same thing is the most important factor, time. So the way to think about how to use this is, assume you had a company that was trying to adopt nanoparticle for treatment of agriculture wastewater, you could decide, hey, if I want my performance to be higher, maybe I need to add more nanoparticles. But no, but what this is telling us is no, you don't need to add more nanoparticles. If you add more nanoparticles, you will get better results. But if you give the reaction more time, that would even make more impact. Okay, so that's how to think about the relative importance result. So technically, that's really true because from the mechanism study, we know that the reactions, the two reactants are feeding back to each other, and that reaction will just keep going until all the reactants are gone. So time is really the most important factor, which tells us that, yeah, the ANN simulation agrees well with what we saw in the experiment. So this is the first study I wanted to go over. And the second one is quite similar, but now I'm talking about soil system, okay, instead of water system. We all are familiar with food recalls. You may have had to return food at some point because, you got a notification from the store that, hey, send this back, it's contaminated with something. And usually something is something like an organism, a pathogen. And many times the contamination comes from metallic contaminants. And this story here talks about rice. So this was last year when Beach Nuts decided to voluntarily recall a batch of rice. And it wasn't just recalling, they also decided to exit the market. They are like, no, we cannot do this. Anybody wants to guess what the contaminant is in that recall? It's rice, so that kind of, it gives it away somehow. Any guesses? Oh, I have charts here. Arsenic, yeah, Pablo, you're absolutely correct. Arsenic was the big problem here. Rice tends to have arsenic for several reasons. But in addition to that one, there were several other issues of food recall last year because of arsenic, because of lead, because of mercury. And, for a company to say, we're not making this product anymore. You know why they said so? They said they cannot see a way for them to sustainably get rice that is free of arsenic. And that's a big statement. So it tells us how serious the problem is. And two of the three recall notices I'm showing you here have to do with food eaten by babies. So it's not just the food consumed by adults that are possibly contaminated. More importantly, foods consumed by babies. And there was a survey last year too. The survey may have started in 2020. They tested 168 baby foods that were available on the market, and you can see at least 95% of them had lead. Well, not just lead, the level of lead was higher than what the FDA recommends to be in baby food. Okay, that's the big problem. And the funny thing is that these foods were still sold. And that particular survey led to several other actions, one of them being the House of Reps summoning the companies that make baby food, the big ones, and say, hey, send us your internal reports. We know you are required to measure metals in these foods. We want to see what you found. And when the reports were sent, some of them complied. Some said, no, we're not doing. For the companies that sent their reports to the House of Rep, the companies' tests also showed that some of their foods had elevated level of metals, but they were still selling the food anyway because those levels were recommended. There is no regulation per se. And one of the resulting actions was FDA coming up with this Closer to Zero initiative, which is just a plan to over time develop some regulatory tool to make sure that the level of metals in food is not at a level that could be potentially toxic. And also part of the initiative is to help farmers as well as food producers to decrease the level of these metals. And a lot of the metals come from when the foods are grown, when the crops are grown. That's when the metals get in. And once the metals are uptaken by the plant, there's almost no way to get it out. Again. So one way to address this problem is to find a way to decrease uptake of metals when crops are grown. So how come we have metals in crops to start with? Well, some of the metals are really in the soil, and some of those metals are just naturally present in soil. Okay, for instance, in the US, this map was published by the USDA about 2 years ago, and it shows the distribution of arsenic in the topsoil all over the US. A big takeaway for me personally is that about 10% of topsoil in the US can have arsenic concentration that is up to 166 parts per million, which is huge. And the fact is, the arsenic may have just been in the bedrock, but anthropogenic activities like farming, construction, mining begin to bring those arsenic to the surface. In addition to naturally occurring arsenic, arsenic can also be introduced to farms through agrochemicals. In fact, back in the day, farmers would actually spray or put pesticides made up of arsenic and lead in the soil, right, to kill pests. But those arsenic and lead weren't going anywhere. They would always be in the soil unless you take out the soil. So some farms still have arsenic from historical uses because metals, as you may know, do not degrade. And lastly, biosolid is rich in nutrients, but it's also a potential source of other persistent chemicals, including metals. So if biosolids are applied in soil, it could be a way to also introduce metals. And in the first study, I talked about recycled wastewater. That could be another mechanism via which metals are introduced directly to crops. So in this study, this second study, the question is, can we still use those nanoparticles to decrease the availability of metals in soil? And the unique thing about metals in soil is, unlike water, you cannot just capture them and take them out. In soil, it's harder to do that. What's kind of feasible is to decrease their availability to plants. In other words, take them out of the aqueous phase and keep them on the surface of a solid. Okay, so you essentially immobilize arsenic or other metals in soil. And we think that if this idea is to be really realistic, if it's going to be used in an agricultural system, there should be 3 boxes to check. One is that the nanoparticle, whichever nanoparticle is used, has to be able to immobilize the metallic contaminants. And we think that most likely the nanoparticle and the metal will form some structure, and that structure needs to be physically and chemically stable. In other words, it shouldn't change over time, because it could change over time, but that change should not lead to remobilization of the metallic contaminants. And lastly, there should be no negative impact on the plants. Otherwise, farmers would never use it. So here is a test we did on the nanoparticles just in soil with no plants. And this is to check the first box. Can these nanoparticles immobilize arsenic? That was our primary target for this study. Can it immobilize arsenic in soil? So here's what we found so far. If we don't treat the soil, actually, to start with, we introduced 50 parts per million of arsenic to the soil. About 37 parts per million was leachable. Leachable means if water gets into the soil, it can wash off the arsenic. So about 37 ppm could be washed off. And with nanoparticle introduction, the amount that was leachable decreased substantially. And if you add more nanoparticle, you get better performance. in terms of immobilization efficiency, this is what the data looks like. And again, if you want more performance, you can add more nanoparticle, but there is somewhat a limit to the amount of nanoparticle you want to add to a soil that you want to grow food in, right? Because at the point, the nanoparticles themselves can start to exert some negative effects. So this data was collected over 7 days, and we think we should be longer than that for us to say confidently that the nanoparticles can actually immobilize arsenic. So we continued that study for about 6 months, and clearly we don't see evidence of remobilization. In other words, the structure formed by the nanoparticles and the metals were stable. But again, this is without plants. This is just bare soil, and we were maintaining the water holding capacity of the soil throughout the study. In particular for SNZVI, we did see increase in the performance over time. And at the end of the day, the difference in the performance of SNZVI and NZVI wasn't really different, but NZVI had a higher immobilization kinetics. We also dug deep into the mechanism of arsenic immobilization. And what we found was, well, arsenic was being reduced from 5 to 3 and 0. And arsenic was co-precipitating with some of the sulfide species in SNZVI. In addition, we saw evidence of arsenic adsorption to the surface of the nanoparticle based on the arsenic 5 peak in the XPS. And just real quick, just wanted to say we did use ANN to also model the kinetics of arsenic removal. And you can see clearly here that the model, which is the lines, compared pretty well to experimental data, which are the dots, and the root mean square error was less than 5% in all the cases. So we checked the first box. Now, does the structure remain stable, particularly when plants are now in the system? And that's important because when plant grows in soil, they release root exudates. Those exudates are acidic. You could have organic acid, amino acids, you could have sugars, you could have all sorts of chemicals. Some of them may be redox active. So do they end up reacting with the composite formed by the nanoparticle and the metal, such that the metal could become mobile again? And that's the big worry. So we needed to answer that question. And here are some mechanisms we think can lead to remobilization. And they are all just reversal of the mechanism that led to immobilization to start with. So this is how we set up the study. We added arsenic to soil. We treated the soil with nanoparticles for about 90 days, I believe, and then we grew lettuce in the soil. So wanted to really see if it works or not. So here's what a picture of the study looks like. This is a greenhouse here at UCI, and Ziwei Han is my PhD student who performed that study. And you can see some of these lettuce really look nice and ready to eat, but sorry, some of them have arsenic in them, and you cannot tell from what it looked like. We just wrapped up the study, so we are still pulling through the data and doing analysis to figure things out. But I'll give you a summary of what we found and then end my talk with that. So here is what the lettuce looks like if there is no arsenic in the soil and there is no nanoparticle treatment. Here is what it looks like when we had a high concentration of arsenic, in this case, 50 parts per million, which is really high, but the plant is definitely not happy, right? And it's making us know that, no, this is not cool. In these other two cases, we also had 50 parts per million of arsenic, but we also had the nanoparticles. So the soil was treated with the nanoparticles before lettuce was grown in there. And you can see that these two plants are way better than without treatment, not as good as the control, but it looks like the nanoparticles are actually doing some good work. On the other side, we also looked at the soil, the amount of arsenic that is leachable before the plant was grown and after the plant was harvested. And we think we found something really interesting there. So in this case, there is no treatment. You can see initially there is this much leachable arsenic. And in the second part is when we have harvested the plants, and you can see that the arsenic concentration that is leachable decreased. Any guesses as to why that may happen? Like why do you think the amount of arsenic decreased after growing lettuce in the soil? Just a guess. I don't really expect you to know the answer, and I'm still trying to know the answer too. But for the sake of time, if nobody is talking yet, we think it is due to uptake of arsenic by the plants. Okay, the plant is gonna take some out, so that may be responsible for the decrease we found. However, when the soil was treated with the nanoparticles, we saw opposite trend in the sense that after the plant was harvested, the leachable arsenic increased both in the NZVI and the SNZVI treatment system. And we think that will be due to the effect of the root exudates released by the plant. And we need to start another study to test that hypothesis. But here's what we found so far. And this is sort of a hypothesis of how the increase in arsenic, leachable arsenic, may have resulted from the exudate released by the plant. So the ligands may be present in the root exudate, can complex with the surface of the structure formed by the nanoparticle, and our metallic contaminants. The ligands are electron donors, so they can complex some of those iron oxides. And if they complex and reduce them from Fe3 to Fe2 state, for instance, there could be phase transfer, which means some of the arsenic that were previously immobilized in the structure of the nanoparticle cannot be released back into the aqueous phase. And with that, I would like to wrap up. The two big take-home messages are, hey, we can manipulate the chemistry of contaminants and NZVI to improve performance without necessarily increasing the amount of the material we use. And secondly, there may be a place for NZVI and SNZVI in the Close to Zero initiative, which is the initiative of the FDA to decrease metal uptake by food crops. And with that, I would like to acknowledge my group, and in particular, Ziwei Han, who did most of the studies I showed you today. And I'll also like to thank you all for listening, and I'm happy to take any questions you may have.
Oh, awesome. Thanks, Yemi. That was a fantastic talk. Yeah, hopefully if the students have any questions and would like to turn on your mic or throw them in the chat. While the students are maybe thinking, I can ask a couple of questions.
Yes, please.
Yeah. I was really, I thought your artificial neural network works pretty cool to predict the pollutant removal. And I was curious if, because it reminded me of, like in disinfection, how you can, either increase the disinfectant dosage or you can let it go for a longer time.
Yeah.
But sometimes they actually lump that together, like they multiply that and then give that as one parameter. Have you thought about maybe lumping parameters to reduce that?
Not exactly. So the way we were thinking about it was from the end user's perspective. So we feel like if this was adopted by a company, they might be looking for ways to optimize their system. And we just wanted to give them the options. Hey, maybe if you just give it more time, it's a cheap way to increase the efficiency to the extent possible. But I agree that maybe manipulating two parameters at a time might actually yield a better result. But we're thinking of it from both the result and the cost side. So what is one thing you can change by 1 unit and get improved performance by 100 units? And in this case, we found that time is the case. But of course, maybe to make it go faster, then yeah, those might be another thing to touch on. And those, I think, is the second most important parameter for, at least for copper removal. So I agree with you, it's probably possible, but I don't think it's something we will delve into too much because it's now taking us away from the chemistry that we really like to study. But I agree with your point, Stacy.
Okay, thanks.
Hey, Adeyemi, good afternoon.
Good afternoon.
How are you? Good presentation, Adeyemi.
Thank you.
Quick question, Adeyemi. So, in terms of the nanoscale technology or practice, what is your experience? Is complex? Is similar to the traditional chemistry, or we have to add a lot of elements that probably it makes this process complex?
Are you talking about the water system or the soil system?
The soil system.
The soil one.
Yeah.
Oh yeah. So I think the way we've done the experiments is probably how it would end up being done. So one, there has to be a mechanism to introduce the nanoparticles to the soil. And in farming, they till the soil anyways. So that might be, it might be during the tilling that they would have done. That might be a good time to also introduce the nanoparticles. But I don't foresee any other factor that needs to change in the way farming is already done, other than to find a way to introduce the nanoparticles. But we are really not at a point where I can say, yeah, these nanoparticles would definitely work perfectly, because like I showed you, they have some effects, and I'm guessing if you want to get more results, you could potentially increase the dose of the nanoparticles. But again, we might be getting to a point where we would also start to see negative impacts. But we haven't figured out that sweet spot yet. But yeah, I don't think it's going to be more complicated than what we've shown in our greenhouse study. I hope I answered your question.
Absolutely, Adeyemi. Thank you so much.
Thank you.
I can ask another question for the NGVI. I was curious, you showed on the graphs that there was a dip where your efficiency was better if you had just NGVI and like the most sulfidized one, but then decreases in the middle. I think I might have missed. Was there a reason why it gives you like a low spot like that?
Are you talking about this right here?
Not that one, actually the copper phosphorus one.
Oh. No, let's go back.
Yeah.
Oh, here?
Yeah.
Oh, okay. So the deep here is, so we were playing around with the chemistry of the nanoparticles, and we were changing the sulfur to iron ratio. And at this point, I don't know why the nanoparticles with the intermediate sulfur iron ratio are not as good. Because we'll have to really look closely at their own chemistry and how they are different from the 0.21, 0.28 ratio. It could also be due to their size, but I really don't know yet. So yeah, sorry.
Yeah, okay, cool.
Yeah, so the one thing we've measured so far is the surface area of each of the different particles we made, but there is also a study that has shown the fact that the proportion of the different iron species is just different. It's not like when you increase the sulfur ratio, it just increases linearly. So we may be forming other species that really just don't contribute to what really enhances removal in the system. But we don't have an exact answer yet.
Okay, yeah, that makes sense. Thanks. So let's see. Raphael, you have another question.
Another question in case if we don't have more questions. Adeyemi, so based on your experience working with nanoparticles, have you seen any other application in the air pollution that probably we can consider that and you can share with us?
Yeah, so I've never worked in air systems, but I have seen colleagues that focus on nanoparticles in air systems, and the extent I have seen is really looking at generation and also using them as catalysts for degradation. So mostly for organic contaminants rather than inorganic contaminants that I am studying. So yeah, that's one potential for nanoparticles, but I don't think NZVI is what I've seen used the most for photocatalytic sort of treatments of contaminants in the gas phase. It's probably things like titanium dioxide. Yeah, so from the treatment point of view, the bulk of what I've seen is degradation of organic contaminants in air. And I think there are people also doing things like carbon sequestration, but that's mostly with adsorption on, say, nano activated carbon as an example.
Okay, thank you.
Yeah.
Thank you, Jimmy.
Sure.
Okay, so if there's no final questions, then let's thank our speaker again. Fantastic talk. And then I guess we can wrap up.
Yeah, thank you all for being here.